highlight more.
No, I wouldn't. I don't even know how to do that.
You say it with a straight face. Okay. We're going to learn about improper integrals today.
I don't like this. I know what improper fractions are. I don't like what this is going to end up being.
Okay. So far in our integrals, if we had if we had definite integrals, we have numbers, right? Okay. And with these numbers, they were always continuous and closed intervals. Well, now we're going to open up the possibility to maybe we don't have a continuous function, or maybe we have some sort of open interval, maybe like a to infinity. Okay, so now we're going to open up the possibility to infinity or negative infinity as a limit of integration, or we're going to open up the possibility to taking a maybe discontinuous function and breaking it into some open intervals so that we can evaluate where we have that discontinuity. Okay? So, hold on, I'm gonna give you some rules here. So let's say we have an interval from a to infinity, okay? Which means your limits of integration are a to infinity. Like, you can't just plug infinity into a function. Oh, but we can do that with a limit. Okay, that's what we've been doing with limits since a year ago. So you can change this limit of integration really to any letter. Okay? R for Richard, N for Nick. I don't care. But you're going to replace infinity with a letter and create a limit using that letter. So you are now have a definite integral where you have a number and a letter. You evaluate the definite integral, and then you have a limit to take. That's why we had to talk about the L'Hopital's rule yesterday, so that we could do some of the integrals from today. Okay. If you have negative infinity, I'm not plugged in. If you have negative infinity as a limit of integration, same thing. We can just replace negative infinity with a letter and create a limit of that letter going to negative infinity. Okay. What if your limits of integration are negative infinity to infinity? You're just going to break it up. Okay? First of all, you're going to choose a nice value in between negative infinity and infinity to break apart your integral. You know, maybe 0 or 1 would be a nice number to break it apart. It doesn't matter. But then you would create two integrals that we would add together. So you would have two limits that you would have to perform.
Oh, and then you just use the other.
Yes, and then you use the rules from above. My goal is to do one of each of these three and then show you a time where 1 to 2 Yeah, 1 to 2 examples of when we have like a discontinuity instead. Okay, so we're gonna start off really simple. No, you're not ready? Okay. You just let me know when you're ready. Okay. Okay, we're going to keep our integration simple as we learn this new concept. If that's okay with you. Okay, so first of all, what does this mean? I want the area under the curve 1 divided by x squared from 1 to infinity. All right. So since we have an infinite limit, we are going to instead replace infinity with b. Sounds great. B for boring.
Hey, that's me.
Just kidding. And we'll say the limit as b goes to infinity. We now have b as our limit of integration of 1 over x squared dx. Okay. Well, what's our antiderivative?
-1 over x.
Okay. So we have the limit as b approaches infinity. Our antiderivative is -1 over x evaluated from 1 to b. So we have, when we evaluate, let's remember the fundamental theorem of calculus. Yes, ma'am.
Okay, just real quickly though, why, like maybe you covered this already and I just didn't hear it or wasn't listening, but from the integral of 1 to infinity, why not just solve the integral and then know that like -1 over infinity goes to 0?
That's what we're doing. You have to do that with a limit though. Like you can't just plug infinity in. You have to think about the limit. What is it approaching as we continue towards infinity?
But why
We can't
not?
just plug infinity in.
But why not?
Because infinity isn't a number. And so we have to put it in terms of a limit so we can think about the behavior of our graph towards infinity.
So the limit is kind of to explain the concept of,
Yes.
Okay.
Yes.
Okay.
Because look, we get -1 over b minus -1 over 1. Fundamental theorem of calculus, right? We plug in the top number minus we plug in the bottom number. Just remember that, okay? So now this is kind of what you're talking about, all right? Now, the limit as b goes to infinity means -1 over b is going to go towards 0. And what's our limit?
1.
Okay, so the area under the curve from 1 to infinity is 1.
That's a really weird thing to think about though.
Right?
Is that really actually like completely accurate? It's like infinitely getting closer to 0.
Yeah.
We say that it converges to 1. So it is so close to 1, we can say it converges to that. Okay?
I just want to take a look at like that graph real quick.
Well, let me just show you what it looks like.
Yep, that's what it looks like. I have to concur.
So it's like 0.9999999.
What if you went from 0?
Then, okay, so 0 is where the asymptote is.
1 over
Yeah.
0.
So then now we have an improper integral with both limits of integration, and I will tell you how to do an asymptote here pretty soon. So can you like say that back?
Can we do this example for the asymptote?
Hold on my phone and set my graphic
Probably not.
calculator.
No. Heard.
I thought you
Okay, now,
No.
Benjamin, how about we go from 1 to infinity of 1 over x?
All of it.
So I guess I'm not doing one of each example. What would you like to replace infinity with?
Q.
Okay, we cannot choose x
F.
because x is already
I
in
want to
there.
use
F.
T. T.
At.
T.
Stop.
Q.
T.
The cucumber.
P is in pterodactyl.
Okay.
S is in city.
Sorry, there were too many choices. I had to just come up with my own.
Okay, but
I'm partial to the letter K.
I was
as in Q.
I was the only one that stopped when you said to stop, so I feel like
I feel like
G as in Nat.
Okay.
I love that word.
what is the antiderivative of 1 over x?
Absolutely value.
So we have the limit as k approaches infinity of the natural log of the absolute value of x evaluated from 1 to k.
that's a lot of lines.
I know. So we have the limit as k approaches infinity of the natural log of the absolute value of k minus the natural log of the absolute value of 1.
Wait a minute.
But-
Wait, infinity minus 0.
Yeah, that's not. It's infinity
Ah,
minus infinity.
what is the limit as k approaches infinity of the natural log? Okay, so our limit is infinity, right? Which means the area under the curve goes to infinity. Okay, since our limit is infinity, we say that this integral diverges. We can't actually we can't put a numeric value on this. It diverges, it gets too big.
And how do we know that again? Just
Because our limit is infinite. So if you get an infinite or negative infinite limit, then your integral diverges.
What does that look like visually?
Well, it'd be like if we took a quadratic and went from 1 to infinity, because it's just getting bigger.
Right. Right. So what what happens is 1 over x looks like this, right? So this just isn't getting close enough to the x-axis, like rate-wise, for us to be able to add up numerically what that is.
Or 1 over x squared did.
Because it gets to the x-axis a lot faster.
I hate this. It's making my head hurt.
Summations.
Trying to
Yeah, we'll get to the
visualize
summation.
these.
Okay, this will help us when we get to chapter 9 next semester. Okay.
Wait, that's next semester.
Yeah, we're not gonna have enough time to do it after this, so I'm gonna save it. All right, my favorite example of the day.
Oh, that's cool. We're going to negative infinity.
when it's like
Write it down.
Stops converging.
This is the bell curve looking thing. Like, but not an actual bell
Bell
curve.
curve is as E and
Yeah, no, we can't do that one. But
Like this.
Is it?
yeah, it looks like a little.
What does a hyperbola look like? Is that like the two?
That's what I just
that are
drew.
Yeah,
also
those.
facing?
Yeah.
Okay, I got that right on the ACT, so I'm happy.
This is a hyperbola right here.
My mom's.
That's the one. So it's not when it goes like this.
It
No,
does.
can
Oh, it
also
does.
be- that's
Okay.
Just, it's just
It's
That's
just
just
rotated.
diagonal. Okay.
All right, so we have two problems with this. We have the negative infinity and the positive infinity. So first, since we have the whole shebang, we have to first split it up. Where would you like to split it up?
a 0.
Okay, have a little bit of forethought. What's our antiderivative going to be?
Is it going to be discussed long?
It's like the arc sine, arc tangent.
Oh,
yeah,
thank
no,
you. Okay.
I'll be honest.
I think
So 7 would not be a great place to go.
Probably true.
Okay? If I'm going to break up this and my antiderivative is going to be arctangent, I think 0 would be a much better choice. So I'm going to break this up. And come on, people, that took you way too long to come up with this antiderivative.
it did kind of look like you were about to have an
You were like punching me in the gut. Like, oh, we can't come up with this.
You're supposed to know.
So I'm going to split this up into two integrals.
There's a lot of integration.
The same antiderivative.
Yeah.
Okay, so now we're going to replace negative infinity. I can actually replace it this time. With a.
What?
And create the limit as a approaches negative infinity. And then I am going to replace infinity with b and create the limit from b to infinity.
Why did we pick 0?
Because it's a nice number in between negative infinity and infinity. It's a nice number to plug in. Okay. All right. So, as a review, our antiderivative for 1 over 1 plus x squared is
Wait, the second derivative says 0 to be 1.
Tangent 1, x squared over 1.
It's just x, I think.
so this was infinity.
Yeah.
I changed it to b and created a limit from b to infinity. We can't have infinity as a limit of integration.
Oh, I was misreading the first one because that looked like 0 to infinity for a second.
Oh,
I like,
got it.
even with my glasses on, my eyesight is not as good as it could be.
Okay.
So
Yeah, it's just arctangent of x
There now.
from a to 0.
What's your-
Chris, thank you for the rules yesterday.
Yeah, I appreciate it.
Okay, so this is where, as a pre-calculus teacher, you might disappoint me, but we'll see.
Very good disappointment.
I will.
Where's the arc tangent?
Hold on.
Oh, is this one of the?
wait, you teach pre-calc?
Yep.
Just everything I've got goes in.
Integration and
Wow. Why would you do that to yourself?
I love it. Okay, do we have this written down?
Almost.
Okay, I evaluated each antiderivative from our two limits of integration. Okay, so let's start with this. What is the arctangent of 0?
This is
Right.
Wait, hold on.
Yeah.
What angle gives us a tangent
0 and
ratio
pi.
of 0?
2 pi.
0 and 2 pi, right? Or no, 0 and
0.
pi.
0. Don't you dare say 2 pi.
But arctangent has a range of negative
54
pi over 2 to pi over 2,
Wait,
so
pi doesn't
only
work.
0.
Tell me that.
Because
Negative
arctangent has a range of negative pi over 2 to pi over 2. It can only come from the fourth to first quadrant.
2 pi is such that.
How'd you know that?
I'm not sure.
Something that we learned in pre-calculus,
Oh,
like I taught
okay.
it to you.
Got
Is
it.
it because of the graph?
Yes.
Was the squiggly line?
What does the graph?
Oh, it's like a weird.
Yes.
Yes. Got it.
The graph will also help us figure out the limit as a approaches negative infinity of arctangent of a, and the limit as b approaches infinity of arctangent of b. So let's just review what this squiggly graph is.
Doesn't it have 2 horizontal asymptotes?
Yeah, it's like
Yeah, it does.
Perhaps pi over 2 and negative.
So Vance,
Notice how the range is negative pi over 2 to pi over 2. That's why our y value had to be 0 for that one. Now, as we go towards negative infinity, what's our limit?
negative pi over 2.
so it's just going to be negative.
And towards infinity,
Pi over 2.
pi over 2. So we have a negative negative. Okay, so we have a positive pi over 2 for this limit, plus a pi over 2 for this limit.
Yeah. So that's just pi.
It's just you.
I don't know. That's just pi.
Negative. Why?
2 pi over 2.
I can still add 2 halves
Oh,
together
okay.
and get a whole. I'm
2
still
is
good
a
enough at
living
math.
number, therefore it is divisible by 2.
Yeah, I still don't
Yeah,
get that.
if only I could speak German.
What do you not get?
We're talking about your proof for like even numbers. Couldn't you just say that it's divisible by 2, like evenly?
That's what the proof
Is it two?
Yes.
I'm making about
Now
like
it's-
conjugation.
I don't think it's a pumpkin.
Pumpkin
Now it's a
pie.
pie.
Apple pie.
Pumpkin pie works too, though.
It's kind of orange,
Yeah, I know the pumpkin.
but that we've kind of ruined
It
it.
looks like a goldenrod apple.
It looks like the apple from English class.
What apple from English class?
Did you watch
the
it
play
class?
today?
No.
It was pretty good.
It was kind of funny.
I like
Do you guys all have the same AP English class together?
I'm in
Like
honors
second level.
English. Thank you very much.
Oh.
I have a fifth.
Did it just-
Yeah, I know.
Yeah.
You
You're
have it
in
with
my
me, but
class.
like everyone else who knows what this
it.
joke is.
You were drinking kale pie with second hour.
Should we write this down?
I already started writing down.
So it is possible that we have discontinuity somewhere in our integral or at the end point of our integral. In which case, we would need to also create a limit at that discontinuity. Okay? Now, if we have discontinuity, like picture an asymptote, can I just say like the limit of that asymptote? It's gonna have to be a one-sided limit, okay? It's gonna be okay, Matt.
Is this where we do the asymptote then?
So what's the issue with this integral? Why isn't it just normal?
Just say when you
It's
plug in one,
undefined at one.
it becomes like
Okay.
not fair.
We have discontinuity at x equals 1. There is a vertical asymptote at x equals 1, which is a limit of integration for us.
Yeah.
So this is this case right here, right? Where we have the left side of our interval is open, right? Because we can't include 1. Okay? So this is what's going to happen.
From 1
We are going to replace 1 with a letter.
Okay.
And we are going to have to create a limit as A approaches
One from on.
from the
Right.
Yeah.
On the right positive.
what?
Because the rest of the graph is to the right.
The rest of the graph is to the right.
Yeah.
I think that's a good way to look at it.
Okay.
Okay, it's your left end point, so everything else is to the right. So we need a right-handed limit. Okay.
Wait, we have to do this like if the okay. So let's say you were doing it from 0 to 2. Would you have to make two of them? Oh, that's just not going to be at all.
Okay, so let's get through this one first before we talk about that. So we have the limit as A approaches 1 from the right. What is our antiderivative?
Negative natural log of absolute value of 1 minus x.
Negative because of that u substitution we would have to do that we can really do in our head, right?
Yes, ma'am.
Or maybe
Was that a question?
wouldn't it just because you take the derivative inside?
Yeah, but if this were x squared, then you can't really use that as a rule. So it's more the u substitution, even though we don't do the u substitution.
No, I don't know. Okay.
Are you not with me?
I thought it was just because the X is negative.
Yeah,
It is because of that.
Yeah.
Because if we did u substitution, u would be 1 minus x.
Yeah.
And du would be negative dx. No, you're thinking about it right. So we have the limit as a approaches 1 from the right of negative natural log of 1 essentially, minus negative natural log of 1 minus a. Oh man.
Oh, is that it?
Natural log of the absolute value of 1 over a.
1 over
1 minus a. Sorry. What's that graph look like?
How? You can't. That isn't. That's not a thing. That's a thing.
It's a thing, it's not a fun thing.
It is.
It's a thing.
The
So it's
natural log of 0?
positive.
Because you have. But you have.
Draw the natural line.
Fine, maybe I will.
Oh, it's negative.
It starts at negative infinity and then
Yeah.
goes
Okay,
up.
that's.
It's negative infinity.
Oh, because the absolute value.
Why equals?
I get that. I get
Okay, so what's happening is we have a shift to the right one. We have a vertical asymptote at x equals 1. We have a shift to the right one. And then that negative means we reflect across what?
That makes sense.
The y-axis,
The asymptote.
the x, y, the x-axis.
Oh, that, yeah.
So,
So just because that's negative infinity, you don't have to worry about it. You just know it diverges.
Say your question again?
Just because that one term is negative infinity, we
Yep.
know it's all going to diverge.
but doesn't it like continually go towards 1? On that graph?
Oh,
So
hold
wouldn't
on.
it be 1?
Something's wrong with this, though, isn't it?
Well, I was just gonna say, if it's 1 positive, then wouldn't it just be the natural log of like 0 positive? Like the regular natural log function, so wouldn't that still be negative infinity?
Say that again.
Like since we did 1, like 1 to the right of 1, wouldn't we
Yeah.
just have natural log of 0 to the right of 0?
Oh, yeah. Which is that negative infinity.
Why is it negative infinity?
This is going to be a tough one.
Okay, it doesn't really matter if it's negative or positive infinity.
But
We know that right here we have an asymptote at x equals 1. And so what happens at an asymptote? It's going to approach negative or positive infinity.
I'm not
So
sure.
regardless, it diverges.
How do we know we have an asymptote? I don't know how you got there.
Because the natural log has an asymptote.
just because.
Well, I know, but I don't know how you.
Can't do the natural log of 0, so.
I just said plug in to the right of 1. Get
How you keep getting like big like smaller numbers, like negative numbers, bigger negative numbers. Is that what you're saying?
What enters the
Like you
group
plug
is
in
like,
3, 4, 5, 6, it keeps getting like more negative.
So
Okay, that's way easier.
just big negative number.
Okay, do we have time for our last example?
Sure.
Okay. I want to address Chris's question.
Oh, okay.
And I promise this has a numeric answer, okay? What is the issue with this integral?
It's not differentiable.
There's two sides.
Remember that.
It's not tasty.
tasty.
Well, there's no infinity, so that's good.
It has
But-
a sharp point. Remember that. No? Doesn't have a sharp
At 1, there's an asymptote.
Thank you. At x equals 1, we have an asymptote because that's where our denominator is 0. It means we don't even have to think about the derivative. All we know is that at x equals 1,
You got a vertical asymptote.
there is a vertical asymptote. So what we are going to have to do is we're going to have to break this up from 0 to 1 and from 1 to 3 because 1 is our point of discontinuity. Okay? And since 1 is our point of discontinuity, then I am going to save some space. I'm going to replace 1 with b and create the limit as b approaches 1 from the
Left. Dang it, I didn't save this space.
You can go to the next line, it's fine. I'm just trying to save space up here. Okay? And then over here, I'm going to replace 1 with a and write the limit as a approaches 1 from the right.
That definitely looks like an email. This is yours. You just went flying. You lost it.
It definitely doesn't.
It definitely did.
Maybe more-
Okay.
Okay, so why is this a left-handed limit? Since we're going from 0 to b, 0 to b.
So if it's
Well, we're going from 0 to 1, and 1
What's the second one?
is the end point. 0 to 1, all of those numbers are to the left of 1. So we're going to do the left-handed limit.
So if it's the top limit of integration, it's to the left, and the bottom is to the right.
Mm-hmm.
Nice.
We replaced a with 1.
Yeah.
Our interval is from 1 to 3.
Wait.
All of the numbers are to the right of 1 in the interval 1 to 3. So that is a right-handed limit. Do I need to go back to B?
You said replace A with 1.
Replace 1 with a. I'm sorry, I said it backwards. This was a 1 and I replaced it with a to
Yeah.
make it a limit
Yeah.
because of the discontinuity.
Yeah.
Okay. So now what is our antiderivative?
Quantity
Negative.
x minus 1 to the 1/3.
What did you say?
Quantity of x minus 1 to the 1/3
Uh-huh.
times.
Something more to that, bud.
Three.
Right?
Yeah.
Okay. See this? These limits are going to be so much nicer than our last one. Okay, so we have the limit as b approaches 1 from the left of 3 times b minus 1 to the 1/3 minus, what happens when we plug in 0?
Negative 3.
We get minus negative 3, like that,
Yeah. Sure hope I did that right.
plus the limit as a approaches 1 from the right of 3 times the cubed root of 2 minus 3a minus 1 to the 1/3.
So, like, technically speaking, could you just use the same variable for both of them?
I wouldn't, so you can separate the two limits. If you have to divide your integral into two improper integrals, I really would choose two different letters. Okay? So if we plug in to the left of 1, this is going to go to,
0.
if we plug into the right of 1, this is going to go to
0.
0. So our integral has a value of 3 plus 3 cubed root of 2. That's our area.
That worked out the bottom.
Okay. Now, we did not encounter any L'Hopital's rule in our 5, 6 integrals, whatever we did, but I can promise you there's at least 1 or 2 in your homework. So please be on the lookout for that. If you get a 0 times infinity or 0 over 0, whatever it may be, please be on the lookout for the opportunities to use L'Hopital's rule as needed. Okay? Tomorrow? We'll get a worksheet? Yep. It's only